In this video, we're going to look at the quotient rule. In the past, we've looked at differentiating algebraic fractions by splitting the fraction up and differentiating term by term. An example might be y is equal to 4x to the power of 4 plus 3x squared minus 7x plus 5 all over x squared. So we'd look at splitting this up. So we could say now that y is equal to 4x to the 4th over x squared, which would give me 4x squared. We'd have 3x squared over x squared, which would just give me plus 3. Minus 7x over x squared, which would give me minus 7 over x, or minus 7x to the power of minus 1, plus 5 over x squared, or we could say 5x to the power of minus 2. Taking the derivative dy by dx of a gradient function, we multiply down by the power and drop the power by 1. So we end up now with 8x to the first power. Differentiating a constant gives us 0. If I now differentiate minus 7x to the minus 1, multiplying down by the power and dropping the power by 1, we get now plus 7x to the minus 2, multiplying down by the power, minus 10x to the minus 3. So this was the derivative, and we did this term by term. What happens though if we have now y is equal to, let's say, 3x over now x, or 2x plus 5. Let's go for 2x plus 5. What would we do here? What if we had now y is equal to the quantity 4x plus 1 to the power of 5 divided by a trig function, let's say cos x? In this particular case, we would use the quotient rule. We can see now that we've got one or more functions of x divided by another. And in general, we can say now if y is equal to u divided by v, where u and v are both functions of x, the derivative dy by dx by the quotient rule is v du dx minus u dv dx all over v squared. So let's see what we've got. We've got the denominator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator all over the denominator squared. So this is what we end up having. If you want it in function notation form, we can say now the derivative with respect to x of f of x over g of x. So these are now just two functions of x. This will give us g of x multiplied by f dashed of x. Then we'll have now minus f of x multiplied by g dashed of x, and this will now be all over, and we'll take now this to be g squared. So g of x squared. So that's now in function notation. I prefer working with this particular form, and we can see that this is quite close in terms of its formation to that of the product rule. Remember, with the product rule, what we had, and I'll just put it over here, we took now the values. So when we had a product, we have the product y is equal to u v, where u and v are both functions of x. We had u, we had du dx, we had v, and we had dv dx. And we multiplied v by du dx and added u multiplied by dv dx. This is similar, but we're going to now multiply these two, subtract away the multiple of these two, and then put it all over v squared. So this now is the quotient rule, and we use this when we are dividing two functions like so. So u and v are both functions of x that we can differentiate. Later on in this series of videos, we're going to dedicate particular videos to both trig and exponential and log functions. For now though, I just want to work through some basic examples. So if we go back now to our example here, we've got 3 over 2x plus 5. There are a couple of ways that you could differentiate this. What I'm going to do is use the quotient rule on this though to differentiate it. So what we'll do is write now that y is equal to 3x, so I've got one linear function of x over now another linear function of x. So what we want to do is find now the derivative. So what I'm going to say then is u is going to be equal to 3x. So we can write this in the form y is equal to u over v. So u will be equal to 3x, du dx, the derivative with respect to x will just be 3. Now at this stage we could have written this like we took out now the constant before. We could write this as 3 lots of now x over 2x plus 5. It's entirely up to you. I've left the constant in. Often it's easier to take it out, but we'll do it with it for now. Let's now take v. v is going to be the denominator, which is going to be 2x plus 5, and then the derivative dv by dx will now be 2. We take the multiple of these two. So what we're doing is writing now the derivative dy by dx will be v du dx minus u dv dx all over v squared. So let's go ahead and do that. What I'm going to have then is the following. I can say that dy by dx will be the multiple of 3 and the quantity 2x plus 5. So we've got 3 lots of 2x plus 5. We're now going to multiply these two and subtract them away. So we'll have minus 2 lots now of 3x. Do be careful with this. If we have a negative, then we're going to end up now with a positive, and we put all of this now over v squared, which is going to be 2x plus 5. So very similar to the product rule in terms of this part, we're just subtracting and putting it now over v squared. So let's go ahead and see what we end up with. On here, we've got now that dy by dx, we're going to have 3 lots now of the 5, which is going to be 15. We're going to have 6x minus 6x, which will cancel. So we end up now with 15 over the quantity 2x plus 5 all squared. All I've done is just expanded. 6x plus 15 minus 6x is just going to give me 15. Of course, you can show your workings as you go. That is one way of differentiating that particular quotient. There are other ways, but that is now an approach that you could take just to get some practice with this. Okay, let's have a go at another one. Let's take now a function of x. Let's say we've got y is equal to 4, and then we'll have sine x. So we've got now a trig function, and then we'll now take 2x plus 1, and we'll cube this. As you can see with this particular case, we've got a function of a function in the denominator. So somewhere in our work, we're going to use the chain rule. So what I'm going to do then is write that dy by dx just here is going to be equal to, and I'm going to take the constant out. We've got now 4 lots of this fraction right here. So what we'll do is just now draw up the table. You certainly don't have to do this table. I like to do it to ensure that I'm keeping my work nice and neat. So we've got u, and u is going to be the sine of x. We've seen from our standard results the derivative with respect to x of sine of x is cos x. We've now got our v, and our v is going to be 2x plus 1 to the power of 3. What we want here is our derivative dv by dx. So I'm now going to apply the chain rule informally. We differentiate the outside function, we rewrite the inside function and multiply through by the derivative of the inside function. So if you haven't seen the video on the chain rule, do check that out as we need it now for this derivative. So differentiating the outside function, we multiply down by the power, we rewrite the inside function, we drop the power by 1 and multiply through by the derivative of the inside function. Derivative of 2x plus 1 is 2. So all I'm going to do is multiply these two. So we're going to have now 2x plus 1 to the power of 3 multiplied by cos x. We're now going to subtract away and we'll have minus 6 lots of 2x plus 1 to the power of 2 multiplied by sine x. So all I've done is multiply this. We've got 6 lots of the quantity here multiplied by sine x, and then we're going to put all of this now over v squared. If I square this, I'm going to now get 2x plus 1, and that will be to the power of 6. I'm squaring this bracket now. This bracket's already cubed, so if we square it, we're going to get now to the power of 6. Okay, let's go ahead and do some simplifying on this. We can see that we can divide numerator and denominator by the quantity 2x plus 1 all squared. So just writing this out, we've got dy by dx, which is the gradient function by the quotient rule, will be 4 lots, and we'll do it step by step and simplified. I'm going to now take out 2x plus 1 all squared. That leaves me now 2x plus 1 multiplied by cos x minus 6 sine x, and then this will all be over now 2x plus 1 to the power now of 4. So all we've done is just divided top and bottom like so. So this is where we end up, and we have this scenario. So this right now is the derivative with respect to x of 4 sine x over 2x plus 1 all cubed. You can of course write this in different forms. You could expand this out, you could rewrite it, but essentially that is the derivative. In some typical exam questions you may get asked to put it in a particular form, but that is now the derivative using the quotient rule. Now sometimes we can use either the quotient rule or the product rule. So let's have a look at an example of that. Let's say we have now y is equal to, and we'll have y is equal to 3 lots of the natural log of x, and we will divide this now by x squared. So we could view this now as a quotient, or we could view it as a product, and we'll do it both ways. Let's first view it as a quotient. So what we'll have now, our little table, and again you don't have to use this table, but it might help you out. So what I'm going to put now is dy by dx, and taking now the constant out, we're going to have 3 lots. We've got now the natural log of x. The derivative, as we've seen, of the natural log of x, which will be du dx. So I'm taking the numerator to be u, the denominator to be v, is 1 over x. If we now look at v, we've got x squared. The derivative with respect to x, dv by dx, will be 2x. We multiply these two. As we can see, when I multiply them, I'm just going to end up with x. I'll do it out in full to begin with. We've got x squared multiplied by 1 over x. This now is v multiplied by du dx. So if we go back, we can say that dy by dx, this is the quotient rule, is v du dx minus u dv dx all over v squared. So all I'm doing is simply taking these. Then we're going to subtract away now 2x, so minus 2x. And again, if that had been now negative, it would end up giving us a positive. Minus 2x for natural log of x, and then we divide this now by v squared. So that's going to now be divided by x squared, which we're going to square, which of course will give us x to the 4th. So let's just tidy this up. We've got now dy by dx is going to be 3 lots. So what we've got here now is x minus 2x, the natural log of x, divided by x to the power of 4. As we can see from here, we can divide through by x, so we can say that dy by dx will be 3 lots, and then we're going to have now 1 minus 2 lots of the natural log of x divided by x cubed. And that is our derivative. So I've done that now in terms of a quotient. What we could have seen that as, though, is a product. And if we do that, let's just put a line here. Let's look at this now as a product. What we'll write, instead of now y is equal to 3 lots of the natural log over x squared, we will write y is equal to now 3 lots of x to the power of minus 2 multiplied by the natural log of x. I've written it this way round such that you're not confusing now the natural log of x multiplied by x to the minus 2. So all I've done is taken this now to be a negative power. So what we can say is the following. We've got dy by dx, again, leaving the constant out, which you don't have to do. Let's just remind ourselves now of the product rule. The product rule, dy by dx, will be v du dx, and then we will add to it u dv dx. So as we can see here, the difference is subtle. We've now got the minus and we've got the v squared. So if we look at this as a product, so let's go ahead and look at that as a product. We will have now our u term. We can take either if we like. Let's take now u. We will have now x to the power of minus 2. The derivative du by dx, we multiply down by the power and we drop the power by 1. So we get minus 2x to the power of minus 3. We take v to be the natural log of x, or we could take v to be the natural log of x. The derivative dv by dx will now be 1 over x. So let's see what we end up getting. We multiply these two, which is going to give me now minus 2 lots, and I'm going to write this, minus 2 lots of the natural log of x over x cubed. Just consider now that that's x to the minus 3. So we're now going to add to this the multiple of these two right here. Now if I look at this, what I've got is 1 over x squared, which is this one just here, multiplied now by 1 over x, which is going to give us now 1 over x cubed. So we can see that dy by dx by the product rule is going to give us 3 lots of minus 2 lots of the natural log of x plus 1 divided now by this common denominator of x cubed. And you can see that that is exactly the same as using the quotient rule. So often you can write now the quotient as a product, and you might prefer to use the product rule to differentiate. The only issue here is your negative powers and making slight slip-ups with that, but it's entirely up to you. Let's now look at another example. So say we were asked to find a stationary point. We know if we're asked to find a stationary point, the derivative dy by dx would be equal to 0. So what we might be asked, it might say now find, and we'll put them here, find stationary point for now, let's say y is equal to, let's take x squared divided by e to the x. So we have now an algebraic function here, and we have an exponential function. In the video on exponential functions, we will combine together lots of different techniques to look at some harder examples. But for now, what we'll do is just find the stationary point of, or the stationary points of this particular function. So with this one, again, we could use the product or the quotient rule. We could write this as e to the minus x and simply go ahead and apply the product rule. I'm going to go both ways, and we'll look at the options on here. So let's now treat this as a quotient. So we'll have u, which is going to be the numerator. Remember, u and v are just functions of x. So as long as we can differentiate them now with respect to x, we can define these now as u is going to be x squared. The derivative du by dx will now be 2x. We will take v will be e to the x. We've seen from our standard results that the derivative with respect to x, dv dx, is e to the x. So we're going to multiply these two, so let's go ahead and do that. We can say now that dy by dx by the quotient rule will be 2x e to the x. We will subtract away the multiple now of these two, which is going to be x squared e to the x, and we will divide this now by the denominator squared, which will be e to the x, which we need to square. So this is going to give me e to the 2x. We know e to the x multiplied by e to the x is e to the 2x. So let's do some tidying. Let's just do a bit of tidying. So dy by dx, firstly we can take out a common factor of x e to the x. So we've got x e to the x. That will leave me 2 minus x, and then we will have this over now e to the 2x. So doing a bit of tidying, we can divide numerator and denominator by e to the x. So dy by dx will be equal to now x, and then we've got now 2 minus x divided by e to the x. So all I've done is divided there. So now for stationary point, let's put 4sp dy by dx will be equal to 0. So all we need to do is consider that this numerator is going to be equal to 0. So let's go ahead and do that. So 0 will be equal to x, and then we'll have 2 minus x. So this tells me that x would be equal to 0 as an x coordinate, or 2 minus x would be equal to 0, which would give me now that x is 2. So if we consider now when x is 0, if we sub this back in, we can see now that y would be 0. So 0 squared over e to the 0. E to the 0 is 1, but 0 over 1 is going to give us 1. So we could say if x is 0, then we've got y is equal to 0. So we've got the first point, which I'll just call point A, and that's going to be 0, 0. So that's going to be the origin. Now if we take x to be equal to 2, we can sub this in. So what we're going to have is 2 squared over e to the power of 2. So that's going to be 4 over e squared. So let's go and put that in. So y is going to be equal to 2 squared, which is 4 over e to the power of 2. Therefore, we'll call this point B. We've got now the point 2, and then we could write this as 4 over e squared, or 4e to the minus 2. Entirely up to you on how you wanted to do it. Just on a quick idea of what this is going to look like, a bit of a guess, our function should look something like so. We'll come round, we'll come to this minimum right here, we'll come up to a maximum, and then it'll do something like that. Give or take, that's what my brain is telling me the function will look like. So this point will be 0, 0. That will be now our minimum. Okay, so let's take this to be the minimum, and then we can have this maximum just here, and that's going to be at 2, 4. and then we can have now e to the minus 2. So that's what we have. So there's, let's write there, max. So that's what the function is going to look like, give or take. And you could get a graphical calculator on that and check that out. Now, of course, we could, if we really wanted, go ahead and look at finding the second derivative and proving that these are maxima and minima, or maximum and minimum points, by taking the second derivative. Now, there's the first derivative, x, and then we've got now the quantity 2 minus x. And that's over e to the x. So if we wanted, we could go ahead and find the second derivative and confirm that this was a maximum and this was a minimum. Now here, it looks like we've got a product, but often it's easier just to expand this out and go ahead and do it term by term. So let's just do this. Let's find the second derivative. So what we've got then, dy by dx, and I'm just going to, instead of writing it like so, you could treat this as a product. I would just expand the brackets. So you've got 2x, and then you've got now minus x squared, and that's over e to the x. So let's go ahead and find d2y by dx squared using now the quotient rule. So just thinking off the top of my head, let's go ahead and do that. So what we've got then is u. So we've got u now is 2x minus x squared. So what we can say then, the derivative will be 2 minus 2x, or 2 lots of 1 minus x. And then we'd have this now as du by dx. I'm just thinking whether it's going to be no quicker doing this as a product. And then we'd end up now with our theta. Let's put our theta, and we've got e to the x. And then the derivative with respect to x dv by dx is going to be equal to e to the x. So we want to now apply the quotient rule for the second time. So what we're going to have, d2y by dx squared is the second derivative. And as we've seen in many units before, we can use this to find maximum and minimum points. So if we now multiply these two, I'm just going to write this now as 2e to the x multiplied by 1 minus x. So I'm just factoring that. That now is 2 lots of 1 minus x. I'm just making it nice and neat. Minus, then we're going to have x e to the x, and then we'll have now 2 minus x. So all I've done here is taken a common factor of x out and multiply these two. You can, of course, do it in a couple of goes, and then we will divide this now by e to the x, which we need to square. So that's now over v squared. So can we tidy this up? Let's go ahead, d2y by dx squared. If I now look at this, if I go ahead, I suppose we could do some work with this. I'm just going to take now a common factor of e to the x out. So we've got e to the x, and then that's going to leave me now just in here. Let's just write that as 2 minus 2x. And then that's going to leave me here minus 2x, so minus 2x. And then we're going to have now plus x squared. That looks pretty. So plus x squared. And that's all going to be over now e to the 2x. I'm just seeing in terms of what this would do. Let's just tidy this up. I'm just sort of thinking out loud here. d2y by dx squared is going to be the e to the x will cancel. So we're going to have now x squared minus 4x plus 2 in the numerator now over e to the power of x. And I suppose you could write that in different forms and make it look a little neater. If you wanted to complete the square, you could do, if you wish, let's just do that, d2y by dx squared. And then we'd have now x minus 2 all squared, and then we'd have now minus 2, and that would be over e to the x. So we could go ahead and test these points. So we could see now that if we had this point right here, so let's go ahead now and take this point here. So if we took 0, 0 and subbed it in, so if I put 0 into here, we're going to have 2 over 1, and let's just do that. So like when we put in here, when x is equal to 0, so that was our first point, we can say the second derivative, d2y by dx squared, is going to be, so if I sub in 0 here, I'm going to get 4 minus 2 over e to the power of 0, which is going to give me now that d2y by dx squared is going to be equal to 2. E to the 0 is 1, 4 minus 2, so that'll give me 2. So we can see from here now that d2y by dx squared is giving me 2. We can say if d2y by dx squared is greater than 0, then we have now a min. If it's less than 0, we have a max. So let's write that there, dy by dx squared less than 0, then we've got a max. So you can see now we're just working with old techniques that we've come across before. So this point right here we can confirm is a minimum. And of course if you want to sub in this one right here, this is when x is going to be equal to 2 for b. So if we sub that in, we can see now that this is going to be subbing in, let's write it just here. So when x is equal to 2, so when x is equal to 2, we're going to have now d2y by dx squared, and subbing in 2, that's going to give me now 0, so we'd have minus 2 over e squared. Now that gives me that d2y by dx squared is less than 0. Clearly it's going to be less than 0. E squared is just 2.718 squared, so we can say therefore that now is a max. So we can see that we can use the second derivative, and I've just used now the quotient rule on the second derivative. So we've shown that those are maximum and minimum points. So that kind of extended this a bit beyond where we want, but again we've got some more practice using the quotient rule. So let's go back to where we started. We use the quotient rule when we're dividing one or more functions by another. So if y is equal to u divided by v, where u and v are both functions of x, we can say the derivative dy by dx by the quotient rule is v du dx minus u dv dx all over v squared. Sometimes we'll need to use a chain rule, sometimes we might need to use a product rule in there, and often you can write these as products. Hopefully that's given you a starting point. In the next couple of videos we will look at specific tutorials on both trig and then exponential and log, and then move on to some exam style questions.